For decades, the development of large language models followed a linear rule. More parameters meant more intelligence. High-tier reasoning and complex logic were viewed as exclusive properties of massive, cloud-based architectures. This is the Arena.ai leaderboard. Google's Gemma 4 holds the number 3 spot with 31 billion parameters. It is competing directly with Qwen 2.5 and GLM-5, models containing 1 trillion and 740 billion parameters. The reasoning scores are nearly identical, yet Gemma is achieving these results while being 20 to 30 times smaller than its closest rivals. This statistical tie breaks the long-standing assumption that high-performance logic requires extreme computational scale. This efficiency shifts the focus of AI development. It moves high-tier reasoning away from massive server farms onto local, offline consumer hardware. To understand how a desktop computer hosts this intelligence, we must examine the architectural layers. First is the math of quantization. Second is effective parameter limits. And finally, sparse neural routing. Raw scale is no longer the primary objective. Architectural efficiency is now the requirement for localized AI agents. Running these models locally requires a specialized software environment, such as LM Studio, to act as the interface between the model and the hardware. Before any inference can occur, the local machine's runtime environment must be fully updated. This engine allows the AI to communicate with your processor. Outdated frameworks lack the instructions necessary to execute modern model architectures. If the runtime is not current, the model will fail to load. Even with updated software, the physical hardware creates a bottleneck, specifically video RAM or VRAM. Uncompressed AI models often require hundreds of gigabytes of memory, far exceeding the 8 to 24 gigabytes found on most consumer graphics cards. To bridge this gap, we are testing the Gemma 4 variant with 4 billion parameters. To function on edge devices, the model's data must be compressed until it fits within the strict memory limits of the GPU. This compression process is known as quantization, and it is the first mechanical step in local deployment. For our local test, we used 8-bit quantization to balance performance with logical accuracy. This process takes the model's neural weights, originally stored as precise 32-bit floating-point decimals, and condenses them into smaller 8-bit integers. Converting the data to integers reduces the overall file size, allowing the entire model to be loaded into the VRAM of a standard graphics card. This is a mathematical trade-off. We accept a slight reduction in numerical precision to gain massive savings in memory usage. While 4-bit quantization exists for lower-end hardware, it involves a much steeper drop in accuracy. We chose 8-bit quantization because it preserves a higher degree of the model's original reasoning capability. Quantization serves as the necessary translation layer that allows data center scale math to run on consumer-grade hardware. Beyond the bit depth, there is an unusual discrepancy in how this model occupies physical space on a hard drive. This chart compares 2 generations at the same 8-bit quantization. Gemma 3 takes up 5 gigabytes. Gemma 4, however, requires 10 gigabytes, exactly double the footprint of its predecessor. The reason for this larger size is found in the E4B label on the file. E4B stands for effective 4 billion. In reality, this model contains 8 billion parameters, but it uses a different structural method to access them. That method is sparse activation. While the full 8 billion parameters are stored in memory, they are not all used at the same time. When a query is processed, the model activates only the 4 billion parameters most relevant to the question. The remaining half stays inactive. This sparse routing allows the model to retain the knowledge depth of an 8 billion parameter system while maintaining the fast computational speed of a much smaller model. Because only half the network is being actively computed, the model can generate 55 tokens per second on local hardware. Sparse architecture balances the conflict between speed and intelligence, allowing for deeper logic without overtaxing the GPU. This architectural efficiency extends to multimodal capabilities, allowing the model to process more than just text. To test its vision, we provided an image of a rare albino rock wallaby, a species often confused with more common animals. Along with the image, we included a text prompt that incorrectly identified the animal as a white ferret, specifically trying to mislead the model's logic. Gemma 4 successfully ignored the incorrect text. By analyzing the visual data, it accurately identified the animal as a wallaby, proving its vision system can override misleading prompts. Processing these complex inputs is supported by a 256,000 token context window, allowing the model to hold vast amounts of information in its active memory. However, this capacity is tied directly to your physical hardware. As the context window fills with tokens, the local RAM usage spikes in parallel. While the software supports a massive context, the physical RAM on your device sets the actual limit for how much data the model can work with at one time. The most significant shift for local models is the ability to initiate actions through toe calling. We tested this by asking the offline model to generate an image of a cat and a dog playing badminton. The model recognizes it cannot natively generate images. Instead of attempting to describe one, it initiates a function call to an external tool. It routes a request out of the local environment to a service on Hugging Face. The service returned an error due to an exceeded quota. The model captured this external feedback and relayed the specific error message back to the user. This communication is made possible by the Model Context Protocol, or MCP, which standardizes how models interact with external tools. Though the image failed, the model successfully demonstrated its ability to act as a routing hub for tasks it cannot perform on its own. MCP tool calling allows a local text model to delegate specialized tasks to external services, expanding its functional capability beyond the limitations of the local hardware. What we see is a powerful system capable of complex, multimodal reasoning running entirely on everyday consumer hardware. This is achieved through 3 integrated layers: 8-bit quantization for size, E4B sparse routing for speed, and MCP for external tool delegation. This architecture provides a fully offline, autonomous alternative to centralized cloud-based AI. Gemma 4 demonstrates that the future of open-source AI is not found in simply building larger models, but in engineering strategically efficient agents for the decentralized edge. Google recently released its open-weight Gemma 4 models, altering the computational threshold for local desktop systems. Until recently, running a large language model with advanced reasoning capabilities required access to centralized data centers packed with high-end GPUs. This chart compares a legacy massive model against Gemma 4. On the left, architectures like GLM5 demand 740 billion parameters. On the right, Gemma 4 requires only 31 billion. Despite the massive gap in structural size, they achieve near-identical performance scores on Arena.ai. The engineering challenge is moving this statistical parity out of cloud testing environments and deploying it directly onto consumer-grade desktop hardware without triggering system bottlenecks. We are going to map the architecture required to run this model fully offline. We will deconstruct the sparse activation routing that gives the E4B model its unusual memory footprint and empirically test its multi-model capabilities. Achieving this level of benchmark parity offline severs the dependency on cloud API providers. It places frontier-level computational reasoning directly under the control of local engineers. To build this local node, we start with LM Studio. This application provides the foundational execution layer for offline deployment. Loading a modern model architecture requires strict environmental compliance. The local engine frameworks and runtimes must be updated to their absolute latest versions to interpret the data structures properly. Gemma 4 supports an expanded context window of 256,000 tokens. Processing that volume of continuous data requires runtimes specifically built for deep memory buffering. Attempting to load 250,000 tokens into active memory will instantly overwhelm standard consumer VRAM limits. The raw data must be compressed. We resolve this hardware constraint by downloading the 8-bit quantized version of the model, specifically the unsloth optimization. This compression strategy reduces the precision of the network's weights to fit within local VRAM. Combining modernized execution runtimes with aggressive 8-bit quantization is the precise formula required to load a frontier-class system directly into consumer memory limits. When you download the compressed 4 billion parameter version of Gemma 4, you immediately encounter a file size discrepancy. Typically, an 8-bit quantized 4 billion parameter model occupies roughly 5 gigabytes of physical storage. Yet the Gemma file registers at exactly 10 gigabytes. It is double the expected density. This diagram illustrates the cause. The architectural designation for this specific model is E4B, which stands for effective 4 billion. The structure physically contains exactly 8 billion parameters. This total architectural mass dictates the 10 gigabyte VRAM baseline required simply to hold the model in memory. During a forward inference pass, a distinct sparse routing process takes over. As data enters the system, only 4 of those blocks engage to process the information. The rest remains strictly dormant. The system dynamically evaluates the query and routes it to utilize only half of its available parameters at any single moment. By calculating a 4 billion parameter pathway through an 8 billion parameter network, the model generates responses at 55 tokens per second on consumer hardware. Sparse activation solves the memory-to-speed bottleneck. It stores a vast analytical knowledge base in your RAM, but computes at the high speed of a localized, highly efficient node. With the textual reasoning pathways established, we can test the system's native vision processing. To evaluate the strength of its visual encoder, we run an empirical stress test using an adversarial prompt. We feed the model 2 conflicting pieces of data simultaneously. We provide an image of an albino rock wallaby, overlaid with a firm text instruction declaring, "This is a white ferret." This forces an analytical conflict. We are testing whether the explicit, false textual context overrides the raw pixel data ingested by the vision encoder. Upon processing the input, the model's first step is analytical refusal. It isolates the visual characteristics and rejects the white ferret text prompt entirely. It then outputs a precise classification, correctly identifying the subject as an albino rock wallaby, despite the adversarial text injection. Legacy models routinely failed this exact test. When processing rare visual subjects paired with conflicting text, older architectures hallucinated the result and deferred to the false prompt. This successful refusal confirms that the local vision encoder is robust enough to process uncurated, chaotic, or incorrectly labeled real-world datasets without succumbing to hallucination. The highest order capability of the Gemma 4 architecture is its capacity to function as an autonomous system node. In a local context, function calling means the model shifts from generating passive text to actively routing commands to external tools. We establish our FIDOS test by prompting this localized text and vision model to generate an image of a cat and dog playing badminton. The model scans its internal parameters and recognizes a strict structural limitation. It lacks the native weights required for image generation. To solve this limitation, it utilizes the Model Context Protocol, a standardized bridge allowing local nodes to communicate securely with external services. This flowchart details the autonomous routing process. The Gemma 4 local node acts as the central router. It formulates a command and transmits a formatted JSON request via an MCP tool call to the remote Hugging Face API. At the remote endpoint, the test encounters a failure state. The external API rejects the call because the user account has hit a quota limit. It fires an error payload back down the MCP channel. Gemma 4 receives this returning data, translates the raw API error into a readable diagnostic, and outputs the result directly to the user interface. Encountering an external quota error is a definitive success for the internal model. It proves the local agent analyzed its limitations, formulated a valid tool call, routed it to the exact external endpoint, and processed the response autonomously. We can now evaluate the complete, multi-layered architecture required for a fully local AI system. This diagram maps the layers deployed. We begin with the consumer edge hardware baseline. On top, we deploy the LM Studio runtime. We load the quantized sparse weights of Gemma 4 and top the stack with native vision processing and agentic MCP routing. Merging aggressive 8-bit quantization with an effective sparse parameter routing mechanism makes this advanced stack viable on mid-tier hardware. This highly compressed local stack achieves mathematical parity with prior generation legacy massive models. Professional-grade, multimodal, and agentic AI capabilities are definitively decoupled from centralized cloud dependency. Engineers now have the architecture to establish sovereign local development directly at the edge.